Welcome to U5L4 Trig applications. So before we get into these notes, make sure that you have these 3 steps written down. So these are the 3 steps I want you to follow anytime you go to solve one of these trig application problems. So you're going to read through the scenario and then you're going to decide what value or values are you looking for. Then you're going to decide where would the right angle be. Sometimes it'll give you a diagram and it'll indicate where the right angle would be, but a lot of times you just have to figure out where it would be based on sort of what would naturally make sense. So for example, a lot of right angles are modeled in real world situations where you have like a wall meeting the ground, or a cliff meeting water, or a sign meeting the ground, or a tree, things like that. Sometimes it could even be situations where you have like something hovering or flying, like a helicopter, a plane, a blimp, something like that, a kite. And then the right angle, it has to do with where that meets the ground, or even like the horizontal, like imaginary horizontal in the air. So think like you have like an airplane right here, and you have like this horizontal distance, this horizontal direction, where it's like flying, and then you have like a distance to the ground, right? And so you could have right angles in both of those 2 places. Okay, and then the third thing is, once you figure those out, you're going to figure out what trig ratio you can use, and then you'll go from there and use that trig ratio, okay? Okay, so looking at example 1, it says, how far from the base of a building must the bottom of a 15-foot ladder sit in order for it to make a 52-degree angle with the ground, round to the nearest tenth of a foot? Okay, so basically, first thing we need to figure out is what value are we looking for. So the question is, how far from the base of a building must the bottom of a 15-foot ladder sit? So how far from the base of a building must the bottom of a 15-foot ladder sit? That's the question. So from the base of the building, which is the bottom of the building, and the bottom of the ladder, which is here, how far is that? So what is that distance? We can go ahead and call it x just to make it simple. So that'll be x. So that's what we're looking for. Now, where would the natural right angle be? Okay, so it'll be where the wall intersects with the ground. So that'll be our right angle. And then we can figure out what trig ratio to use. So just want to point something out real quick before we do that. It already labeled the information for us in the diagram. So it labeled the 15-foot ladder here. And it says here, in order for it to make a 52-degree angle with the ground. So 52-degree angle with the ground. So where the ladder intersects the ground is going to be 52 degrees. Of course, it gave it to us here, but in the future, you'll have to be able to label that yourself. Okay. And then it looks like if we label our values for HOA, we have the hypotenuse is 15. O is the brick wall, and adjacent is X. So we're looking for cosine here. Okay. So cosine of my reference angle of 52 degrees is equal to A over H. So X over 15. Solve for X by multiplying by 15. Make sure your calculator is in degree mode, and then just multiply 15 times the cosine of 52. And you should get about 9.2349, etc. It says round to the nearest tenth of a foot. So it's going to be X equals 9.23. Rounded to the nearest tenth is going to be 9.2. And the units here are feet, just like it says 15 foot ladder. So feet. Okay. So then the answer here would be the base of the ladder, or the bottom of the ladder, is 9.2 feet from the base of the building. Okay, so the answer is 9.2 feet, but sometimes you will have to write out sort of the scenario or the context, and so that's what I did there as well. All right, example 2. Ariel is standing 47 feet away from a Christmas tree that is 29 feet tall. Ariel looks up at the top of the tree. What is the angle of elevation of the top of the tree? So Ariel is standing 47 feet away from a Christmas tree, and that Christmas tree is 29 feet tall. Ariel looks up at the top of the tree. So here's the question. What is the angle of elevation of the top of the tree? Okay, so first things first. We're looking for an angle of elevation, but what the heck is an angle of elevation? So an angle of elevation, let's go ahead and write this down. Angle of elevation equals the angle from horizontal up. Actually, here, let me write this a little bit neater. Angle from the horizontal up. So for example, if you have a horizontal distance of any sort and you're going up, it doesn't matter on which side, that is an angle of elevation, okay, going up. Perfect. Okay, so the angle of elevation, if we look at the scenario, we have a Christmas tree. Ariel is standing away from it. So this is Ariel. This A is Ariel. The angle of elevation is going to be looking up, from the ground up. So the angle can be best represented here. I'm going to call it theta since we usually use theta for the angle. So that's what we're looking for. We're looking for that angle of elevation theta. So that's what we're looking for. So we're not looking for a length or a distance like before in question 1, right? We're looking for this angle now. And then there's a couple things that we need to put into the diagram. So the right angle is already there actually, right? That right angle here where the Christmas tree meets the ground, that's already there. But we do need to put in the value. So she's standing 47 feet away from it. So that's AC. This is 47 feet, the distance she is away from it. And then it's 29 feet tall. So that's going to be CB. So that's 29 feet tall. And we're looking for the angle. So we have 2 values. So it looks like we can use our reference angle of theta, which is the one we're looking for. And then we don't know the hypotenuse. We do know the opposite side, which is 29, and we know the adjacent side is 47. So we can use opposite and adjacent, which is going to be tangent. So the tangent of theta, which is the angle we're looking for, is equal to O over A. So 29 over 47. And then, of course, we use our inverse tangent to find our value of theta. So our inverse tangent to find our value of theta. When I plug that into my calculator, inverse tangent of 29 over 47, I get about 31.6 degrees. I'm going to go ahead and round to the nearest whole number because it doesn't say what to do, and that's what we usually do when we do angles. So I'm just going to put 32 degrees, round it up to 32. Okay. So the context here, the angle of elevation from Ariel to the top of the tree top of the tree is 32 degrees. All right, next one. So looking at example 2, a lighthouse in Cape Hatteras, North Carolina is 200 feet above the sea level. If it spots a boat that is at an angle of depression of 28 degrees, as shown, what is the horizontal distance to the base of the lighthouse? Round to the nearest foot. So first of all, let's write what a angle of depression is, because that is going to show up here. It's kind of like an angle of elevation, except kind of the opposite. So angle of depression, let's write this down at the top, is the angle from the horizontal, angle from the horizontal, but instead of up, it's down now, okay? So angle of elevation, elevating means going up, so that's from the horizontal up. But depression means going down, so an angle of depression is from the horizontal down. So anytime you have any horizontal distance and you're talking about an angle of depression, it's going to be going down from that horizontal distance, okay, or direction. All right, so now let's figure out what question it's asking. So it says that the lighthouse is 200 feet above the sea level. I'm going to underline that. Okay, that's a lighthouse. It says if it spots a boat that is at an angle of depression of 28 degrees, as shown, so here's the question. What is the horizontal distance to the base of the lighthouse? So from the boat to the base of the lighthouse. So from the boat to the base of the lighthouse. So what is this horizontal distance? I'll go ahead and call that X. So we're looking for a distance again. Now they already labeled the angle of depression. So the angle of depression is from this basically imaginary horizontal line here down. Okay, so that angle of depression is 28 degrees. And if we kind of take a look at where the right angle would be, okay, where the right angle would be, it would be where the lighthouse meets the water. Okay, so that would be our right angle. That means that our triangle is the lighthouse, the water, and then to the boat. But that 28-degree angle is not in that triangle. And so it's not really useful to us right now. But the good news is we can easily put it in the triangle. So we have this horizontal line at the top that we drew for the angle of depression. We have a horizontal line at the bottom. Basically, the water can be represented as a horizontal line. So those are parallel to each other. So if we think back to when we did transversals, we know that this 28-degree angle is one of the interior angles, and the alternate interior angle to it would be down here by the boat, but inside of the triangle. So those are both going to be the same. So anytime you have an angle of depression, then you can put it, if it's not already in a triangle, you can actually put it into the triangle using alternate interior angles. Okay, so we can put the 28 degrees here as well. Okay, same as this one, and that's because of alternate interior angles. Okay, that's why we can do that. Okay, perfect. So now we have the 28 degrees in there. There's one other thing that I underlined, but we didn't put in the diagram yet. And then we can figure out which trig ratio. So it looks like we didn't put in the fact that the lighthouse itself is 200 feet above the sea level. Okay, so 200 feet above the sea level. So that's going to be the height of the lighthouse, basically. So that's 200 feet over there. So now we have an angle here. That was an angle of depression, and then we moved it. Okay, we're looking for this horizontal distance, and we have this height here. So if I use the 28 degrees as my reference angle, I have nothing on my hypotenuse, so I don't need that. My opposite side is the 200 feet, and my adjacent is the x, which is what I want. So O and A is going to be tangent. So let's go ahead and do the tangent of the 28 degrees is equal to the opposite side of 200 over the x. And then to solve for x here, I showed you guys a shortcut. Since we're going to multiply by x and divide by tangent, you can go ahead and just switch spots there. So x is going to be 200 divided by the tangent of 28 degrees. So go ahead and just put that in your calculator. So it's going to be 200 divided by the tangent of 28. And so the answer is going to be x equals 376.1, but it says to round to the nearest foot if I go back and read the problem. So that means to the nearest whole number. So that's going to be 376 feet. Okay, so we can say the boat is 376 feet from the lighthouse. Perfect. All right, this last one's going to be a little bit of a challenge here. Challenge question, not because it's difficult, but because you have to make sure that you do the entire problem correctly, and there's multiple parts. Okay, example 4. A helicopter is flying at an elevation of 575 feet directly above a horizontal highway. 2 motorists are driving cars on the highway. The angle of depression to one car is 28 degrees, and the angle of depression to the other car is 35 degrees. How far apart are the cars to the nearest foot? So the question here is the one I just read. How far apart are the cars to the nearest foot? So how far apart? So from one car to the other car, what is that distance here? Okay, what is that distance? So I could call that x, for example. Okay, but I do notice something. So before we get into all of the actual numbers and trig and everything, let's figure out where the right angles would be. And this is where hopefully you'll notice something as well. So the right angles would probably be here where this 575 height meets the highway, right? So I can actually have 2 right angles here. But what it looks like then is that this problem is split into 2 right triangles. We have the one on the left, the one that looks slightly bigger, and the one on the right. So that means that that x value is really broken into 2 values. So maybe what actually makes more sense is calling one of them x. So the one on the left I'll call x, and that'll be the distance from the car to sort of this middle point. And then on the one on the right, I can call y. So I can call this one y. And that means that what I'm actually looking for is x plus y. So I'm looking for those 2 individual distances added together, okay? Added together to make the whole. So this individual distance plus this one would equal our x plus y. And so we just have to find x and y. We basically have to look at both triangles separately. Issue right now is we do have one length here of, the 575. That's the height there. And that actually works for both triangles because it'll work for the one on the left and the one on the right, right? Because it is a shared side between those 2 triangles. But our big issue here is that these angles are not in the triangles right now. But if we use the same idea of what we did with the angle of depression in the last problem, we can put them in there. So we have our angle of depression of 28 and our angle of depression of 35, and we can put them into the triangle. So alternate interior angles would tell me that that 28 is also going to be in the bottom left. So that's 28 as well. And that this 35 here would also be in the bottom right over there. So that's also 35. Okay. Let me move this y over a little bit. I don't want to confuse you guys. Okay. So there we go. So now I can figure everything out. So I'm going to do the triangle on the left. So I'm going to separate these. So I'm going to do the left triangle separate from the right triangle. Okay. So for the left triangle, let's see what we have. We have our reference angle. We have nothing on the hypotenuse. The opposite side is that 575. And the adjacent side is x. Okay, so tangent. So the tangent of 28 degrees equals 575 over x. And then just like we did on the last problem, this ends up being very similar. These are going to change spots when we multiply by x and divide by tangent. So we get x equals 575 over tangent of 28 degrees. So work that out. And it says to the nearest foot, which means whole number. This means whole number. So I'll go ahead and do this to the nearest whole number. So 575 divided by tangent of 28. That is going to be approximately 1,081 feet. Okay, I just put that in my calculator. And then we need to do the same thing with the one on the right. Okay, so that gives us x. So now we do the same thing with the one on the right. So now we're going to do the right triangle. I don't mean like an actual right triangle. I mean the one on the right, which is the other one, which is this one here. Okay, so we have our reference angle of 35 degrees. Again, we don't have h, so we don't need to worry about it. And then we have opposite side again is 575. This time the adjacent side is y. So we're looking at the tangent again, because we have O over A of 35 degrees equals O over A, which is 575 over y. And then same way we solved before, we're going to get y equals the 575 divided by the tangent of 35 degrees. And that's going to be, let me work that on my calculator, 575 divided by the tangent of 35. And that's going to be about 821 feet. Okay, make sure you're careful when you round. And then to find the distance between those two cars, or how far apart those cars are, we just add them up. So we just do x plus y. So it's going to be 1,081 feet plus 821 feet. Add them up. So 1,081 plus 821 is going to be approximately 1,902 feet apart. And I'll just leave it like that. Okay. So one's a little trickier, but not too difficult. All right. Thanks for watching, everybody. Have a great day.